Welcome to the CS 320 lecture on Chapter 3, Recursive Definitions. So we're going to teach a new way to define languages, which you're probably pretty familiar with, and that's recursive definitions. So this is a recursive definition of even. If 2 is even, if a number, and we'll call it x, is even, then so is x plus 2. Now, there might be another rule, but we mostly won't include this, but a rule to say that nothing else is in even. So only the elements that can be created by these two rules are in even. So usually, if you're going to create your own recursive definition, it's just kind of implied this third rule. So using this third rule, what if we want to or using these rules, what if we want to prove that 8 is even? So what we'd start with is we'd say 2 is even by rule number 1. Then 4 is even. And I'm going to call this step 1. And we could say by step 1 and rule number 2, because 2 isn't even, so we can substitute 2 in for x and get 4. And then we can move on to the next one. 6 is even by step 2 and rule number 2, for the same reason that 4 is even. And then finally, we can say 8 is even by step 3 and rule number 2. So by the way, this is step 2 and step 3, step 4. So basically this rule says we know 6 is even, so we can plug 6 in for that and we can get 8, and so therefore 8 is even. So there's a short little proof proving that 8 is even using this recursive definition. So here is a recursive definition for positive numbers. At 1 is positive. If a number is positive, so is that number plus 1. We can even use real-world examples, like the children of Adam are his descendants, and if X is a descendant of Adam, so are X's children. So if we applied this rule, then everybody here today would be a descendant of Adam. Now the book has more examples of recursive definitions, but we're going to focus on this example in the book, arithmetic expression, that it says is an important language. So why is arithmetic expression so important? Well, it comes down to a compiler in a computer on your programming languages. Our programming languages have to understand arithmetic expression so it can do the addition and subtraction and multiplication. So this is important because this recursive definition helps us write a program that recognizes arithmetic expressions so that we can build a programming language that people can do math in. So here are the rules. Any number is an arithmetic expression. If x is an arithmetic expression, we can put parentheses around it. We can put a minus sign in front of it, but only one minus sign. We don't want two minus signs in a row. And then if x and y are an arithmetic expression, then so is x plus y, x minus y, x multiplied by y, x divided by y. And we have this one here, which is x multiply y, or star star y. And in most programming languages, what that means is it's x to the power of y, or an exponent. Now, if you notice, the book also clarifies that we do not want two plus signs or two minus signs in a row, so y cannot start with a minus sign and then we can include another minus sign in front of it. So we'd have to simplify our arithmetic expression before we type it in to our programming language. Now, if you notice, we are focusing only on the syntax here. And we're not going to worry about what it means to subtract or add numbers or to even multiply or exponent. We're just concerned about what do you have to type in exactly to allow the computer to understand your arithmetic expression. So this is how we're focusing on the syntax of a language and not the semantics or what it means. And in fact, if you read the proofs that go along with this arithmetic expression, the proofs always deal with the syntax. The first proof is for Theorem 2 that says that an arithmetic expression cannot contain a dollar sign. So if you read through the proof basically says, well, a number does not have a dollar sign in it, so that can't introduce a dollar sign into the language. And then in rule 2, there are no dollar signs inside of the language in the syntax, so they can't introduce a dollar sign. And in rule 3, once again, there are no dollar signs in any of the rules that can introduce a dollar sign into it. Therefore, there's no way to get a dollar sign in arithmetic expression. Now let's move on to Theorem 3 that states that no arithmetic expression can begin or end with the divide or a slash. So I'm going to just call this a slash. And the proof of this is, number one, no number has a slash at the beginning or the end or even inside of it. So obviously a number cannot begin or end with a slash. And then in rule 2, there are no slashes. And in rule 3, there are no slashes except for this part 4 is the only place that has a slash. Well, since x is an arithmetic expression, and we know a number can't start with a slash, and in this case where we introduce the slash, there has to be some arithmetic expression before it and some arithmetic expression after it. So the only step that can introduce a slash requires that there's something before and after the slash. And for that reason, we cannot begin or end an arithmetic expression with a slash. Now let's look at Theorem 4 that says that you can no arithmetic expression can have the substring of 2 slashes. So in the book, it covers this proof by doing a proof by contradiction. So I'm going to kind of explain that proof by contradiction. And it says, let's assume that some word created by these rules, this recursive definition, has a double slash in it. Okay? We know that the word was created by following these rules. So let's go back to the step that created the 2 slashes in a row. So let's assume that some word has 2 slashes in it. That word had to be created by this, and on one of the steps, suddenly 2 slashes appeared. Now, once again, the only place where another slash can appear is in this part of our definition. So we know that the x, which is an arithmetic expression, cannot end with a slash because of Theorem 3. And we know that y cannot begin with a slash because of Theorem 3 as well. So if that rule that introduced 2 slashes into our string, it has to be this rule, but we know that it can't happen because of Theorem 3 says an arithmetic expression cannot begin or end with a slash. So therefore, there's no way that these rules could have produced that string that I assumed was an arithmetic expression. Therefore, that string is not an arithmetic expression. So that's kind of a summary of the Theorem 4 proof.